Okay, good afternoon, everyone. The topic of our work is feature space transfer for data augmentation. And we mainly use object post information to achieve this transfer. This is a joint work with my collaborators, Xudong, Mandar, Roland, and Nuno. The main drawback of modern image classifiers is that they are trained with images that have canonical poses. Here are some typical examples from an ImageNet class. Most of them are in a near frontal pose. This problem is common when objects have well-defined frontal pose. Models trained on such biased data will fail to generalize to unseen poses. The problem is even more aggravated in few-shot learning, where it is typically impossible to find all poses of an object represented in the training set. For example, the model learned on the top few images will definitely not generalize to the bottom ones that are captured in completely different poses. So we need a mechanism to handle multiple poses during inference stage. This can be achieved by learning to project an unseen pose into a canonical pose. Alternatively, we can enable the model to simulate different poses starting from a frontal pose as a form of data augmentation. Let's consider the problem in a latent feature space. We have feature representations corresponding to different poses in an object class that induce a topology. We call this a pose manifold in feature space, which contains all pose structure information we need. Images from different poses of a certain object will produce a pose trajectory on the manifold. If we could learn a pose manifold and find a trajectory with all poses, then we could handle pose variability during inference by means of transfer. One strategy would be to map an unseen pose along the trajectory to canonical examples seen during training. This can be referred to as pose normalization, and in fact, this is exactly what a CNN tries to do with limited success. Alternatively, different unseen poses can be generated in form of synthetic data points along a learned trajectory. This leads to a form of data augmentation that enables us to learn better recognition models. In fact, this strategy is particularly well suited to tackle few-shot learning problems in which we are interested in. While knowledge of pose trajectories can help to address the problem of pose bias, these trajectories are non-trivial and inherently difficult to learn. Our analysis finds that pose trajectories of objects in existing CNN feature spaces are complex and highly irregular. Also, as illustrated in this toy example, different instances of a class exhibit very different trajectories. One way to simplify pose trajectory learning is to disentangle actual pose from appearance-related confounding factors. Let's illustrate the key idea here. Given a feature point x from an object in a particular pose, we aim to learn a pose transfer function that leverages the pose trajectory. This transfer function maps x to a point x hat that corresponds to a desired change in its pose. Disentanglement of feature x into an appearance and a pose component, as shown in the illustration, will simplify learning of such a transfer function. This is the goal of our work. First, we project x into appearance and the pose space. We refer to this as the encoding step. The pose component can be changed to a desired value while retaining the appearance component A of x. In the decoding step, we recombine the new pose with the appearance component to reconstruct a new data point x hat. The transformation f of x from the original sample x to the new point x hat amounts to traversal along the pose trajectory. We implement this strategy via a neural network model, which we call the feature transfer network, or FATN in short. The information flow is as follows. First, the input x is a feature extracted at certain layer of a CNN model. Second, to implement the encoding step, x is propagated through a pose predictor and an appearance predictor. Here, A of x and P of x are the appearance and pose components, respectively, concatenated with an encoding of the desired pose. This produces a disentangled representation of the original feature x. The decoder then estimates the residue required to obtain x hat, corresponding to the desired change in pose. We found that, in general, this leads to more stable learning behavior, faster convergence, and overall better performance. To train this system, we need a loss function that ensures the desired pose is realized by the synthetic sample x hat while retaining its semantic identity, for example, the object class label. First, we need a pose loss to encourage the desired pose. Second, we need a category loss to encourage the same category label as the input sample x. Both predictors are pre-trained separately and fixed during the training of the whole model. Note that the pose predictor used in the encoder is the same as the one used to evaluate the pose loss. Finally, combining all of those parts, we obtain the FATN architecture. The exact training details are in the paper. Let's have a look at some experiments. First, we evaluate the quality of FATN-based data augmentation in a retrieval setup on ModelNet. 3D objects are first rendered to 12 different views. Synthetic examples are then used to retrieve instances from these rendered images. This allows us to assess whether we can retrieve images of the desired class and pose. Some retrieval examples are shown here. The first query column shows the original image, while the second column is the desired image corresponding to the query. The results here clearly show that generated features are close to real features. Second, we carried out a data augmentation experiment in a few-shot learning setup. This is what our algorithm is mainly designed for. In this experiment, we have objects from different poses, but data in few-shot learning can't cover all poses. So data augmentation by pose is critical here. We replicate the setup of AGA for 1 and 5-shot recognition on the Sun RGBD dataset. In addition to pose, FATN is used to synthesize depth features to be consistent with the AGA experiments. Importantly, this also shows that our model can be used on attributes other than pose. Compared to a baseline that is only trained on single instance from each class, as well as AGA and the hallucination approach of Hariharan et al., FATN shows the best performance. Notably, feature hallucination is a non-guided approach and doesn't use pose or depth information during training. AGA, on the other hand, uses the pose information but learns a pose trajectory in an inefficient manner. Here is the 5-shot case. The performance gains are similar in the few-shot case as well. Thank you. The full source code are available. Remember to visit us in the poster session H17 for more details.
Any question? So I have one question here. So there is a paper from Jeffrey Hinton's team maybe from 2006. So it is one of his first capsule paper. So are you aware of that paper, and how do you think your method is related?
Maybe I don't know where the paper, but I will think about it later. Maybe discuss in the poster session. Yeah, sounds good. Okay.
So yeah, let's thank the speaker.
We're still missing quite a few spotlight speakers. If you are planning to give a spotlight talk, please come forward to the front seat. Okay. And our second paper is about analysis of the moments of deep networks. And the paper is by Adel, Bibi, Modar, Alfadly, and Bernard Ghanem. And Adel will give the talk.
All right. Hello all. Good afternoon. I'm Adel Bibi, and this is a joint work with Modar Alfadly and Bernard Ghanem from KAUST, Saudi Arabia. And I'm going to talk to you today about some analytical expressions that can be used to analyze deep networks under Gaussian inputs. All right. So there is an uncouth behavior that we have been experiencing the past few years, in which it seems that it is easy for people to actually generate adversarial attacks. And by that I mean, given a network and given an input image, let's say the network is doing classification, is doing very well in classifying that panda correctly. It seems that it's somewhat, there are several approaches in which you can generate small imperceptible noise that once added to panda, all of a sudden the classifier goes crazy and classifies this panda as gibbon. So there are lots of works on this, like in non-targeted attacks and targeted pixel attacks, and people have also shown that there are methods where you can just corrupt a single pixel and that will completely destroy the classifier's performance. Even more interestingly, people have also shown last CVPR that there exist these deterministic samples that once you add them to any input image, you can just completely destroy the classifier's performance. And this does not necessarily have to be sampled from some distribution. And there are also empirical studies that shows that these samples are agnostic from the network architecture as well. So you can take the same exact input image, apply it to any input image to any classifier you wish, and you just destroy the classifier's performance. So this, intrigued so many questions on why does this actually happen. I'll try to tackle this problem from a slightly simpler approach, and maybe this approach will provide us with some mathematical expressions that help us understand what's really going on there. So we'll start with the assumption that the network is actually made up of nonlinear activations, and these nonlinear activations are precisely Wheeloos in order to force the networks to have this piecewise linear sort of structure. So the simple question that one would ask is, assume that you have a noise sample from some distribution G. This network is nothing but a function that generates some U random variable that has a U distribution. And the simple question is, what is this PDF distribution? And if we cannot find a closed form expression for that, can we find the closed form expressions for the output mean and output variance for such a network? Now, it seems that even under simple assumptions like having Gaussian input at the input level of the network, which is one of the most stable distributions that we know, we cannot actually get a closed form expression for arbitrarily deep network. And we particularly believe that there might not even exist such a solution with respect to some elementary functions. So what can we do there? Because the problem seems just too difficult. One way to do it is just to look at bottom-up approach. And you ask a simple question. You say, for how many layers can I derive these closed form expressions? And we were successful to some extent to derive these expressions for a very small network that seems to be practically useless, right? Just affine, ReLU, and affine, right? And so it's given in the expressions g of x, and then x is assumed to be Gaussian, right, with some mean. And that mean could be any arbitrary image. Great. So, so the paper structure is followed that we present two theorems. The first theorem would discuss about what is the expression of that mean for this small particular network. And the second theorem will talk about how would we derive the variance. So with simple analysis with probability theory, I mean, one could derive the expectation of gi of x, where I is just simply the ith function at the output level. Great. Now, the variance is slightly more trickier, and we represent it with the following technical lemma. So there are other results. I'll just keep them to the poster session. So what this lemma tells us is the following. Assuming you have some nonlinear map psi, and under the very mild assumption of this function psi, which in this case would be our small function, which is max linear, ReLU linear, now you can relate directly with an inequality the expectation of this psi under Gaussian assumption with respect to the covariance parameters of the matrix. And that is exactly equal to the expectation of that function with respect to the input variables. So you can think about this as a differential equation, and once you are able to solve it, you have access to your expectation of psi of x. Now, why do we need it to be piecewise linear from the get-go? It is because you can imagine psi of x. You can think about a ReLU. If you take second derivative of it, you get Dirac delta functions, and the right-hand side becomes trivial to evaluate. Right, so I have to emphasize now that this is a result that is extended from a paper published in the Transaction for Information Theory by Roper Price, and to our surprise, it was published in 1958, and these results just keep popping up to be extremely useful in the deep learning community. So, I mean, with a couple of other few results, now we can actually figure out what the closed form solution for the second moment of that small network as given in this form. Now, this is overwhelming from the slides, but we can parse it at the poster session later down there. All right, so great. So what do we have now? Practically useless network where we have some expression for it, where we have expressions for the mean and the variance, right? Great. But how is that useful? Okay, so now what I'm going to talk about is how would we extend arbitrarily sized networks into this particular form, and the idea is very simple. So we start from a network of your favorite choice, trained, so we don't do any trainings, and what you do next is say, okay, so let's say this network has D output functions, so it has D classes of some form, and all you do is you select a ReLU of your favorite ReLU in that network, right? And then what you do is simply you perform what we call a two-stage linearization. You linearize everything after the ReLU, and you linearize everything before the ReLU. And that will precisely give you the structure we're looking for, where the linear parameters are described by the Jacobians of those two linearizations. So now what we'd like to do is use these expressions that we know for the smaller network in order to infer something about the bigger network. Okay. So first of all, I will bore you with some tightness verifications before going to some of the exciting experiments at the far end that relates to some nice applications. All right, so a simple experiment one can do is Monte Carlo estimates of these expressions is basically you generate any random network, fully connected or convolutional if you wish, and we have varied the number of layers on depth layers on that, and we compared the analytical expressions with Monte Carlo estimate for the mean and variance. And these plots, you see the slope, which is 1.0, so the closer it is to 1, the better the performance in general. Great. So another question might be is, okay, fine, so the ratios or slopes are close to 1, but are they, do they actually preserve the ordering score in networks? So in classification, sometimes we don't really care about the exact score, but we care about the ordering in order to infer the class label. And this, as we did this experiment, for example, on AlexNet, where for the first bar you see top 1 accuracy, you see how much these expressions predict the location of the maximum score across the complete validation set. And it does it with a 98% accuracy. And we do it for a top 5 accuracy, which reaches about 80%. Now, the metric we're using is very, very strict, and that's why 80% in fact is very good. Okay, so there are plenty of other experiments that I don't have time nor space to present them about tightness on LINET, what choice of ReLU do you have to make for better performance. Linearization cannot not necessarily have to be done with every single input. You can also now visualize, you can now plot these expressions as a varying variance level at the input, which you see in the x-axis, and see how these logics interact with each other. Okay, that's for the poster session. So let's do some nice experiments. So the first experiment is, can we infer something about the sensitivity of the network using the expressions directly? So think about your covariance matrix. If you made it sparse with except for few pixel locations, those will be exactly the pixel locations that will be corrupted in your image, right? So what we're going to do is basically we take an image, let's say a 1 in this case, and we're going to evaluate the expressions, the output mean, for every single class label under sparse covariance matrices, and the non-zero locations of these sparse covariances are precisely the pixels that we want to corrupt. And we simply look if the maximum score existed in somewhere other than the correct class label, and this is what you see in red. The red location are locations predicted that once you add noise at this location, it will flip the class label, and completely using no forward passes, just evaluation through the expressions. And this is what you see with the class label 1, that you see red regions at the top part, and this makes sense because a 1 in that case would look like a 7, and so on and so forth. Great. So the next experiment would be something even nicer, which is you can ask a different question. You say, okay, fine. We have these expressions for the mean and variance. Now, can we optimize for the input mean and input covariance of the Gaussian matrix such that if I have an input that is a 9, the output classification score for it should be something else? And this is what we call targeted adversarial attack. So I want the network to classify all 9s on average as a 2 or 3 or a 4 and so on. So what we do is simply we maximize the difference between the expectation of the correct class label with respect to all other class labels. So J here is the incorrect class label, and we want to make that as high as possible. And again, so E is the expectation where the mean is the image 9. So once you optimize that, of course, you have to put some boundaries on what the variance should be, because you don't want this to go to infinity and so on. So you can actually now design a distribution parameters in which once I sample from this distribution, on average, we're going to fool the network to the particular targeted class. Something even more interesting you can do is to say, okay, I don't care about targeted class, but rather all I care about is fooling the network to any arbitrary class with alpha% support. It means I will select random pixels in the image. I say, okay, those random pixels I want to corrupt. I just want the distribution parameters, Gaussian distribution parameters at the input, such that once I sample from that distribution, on average, I will flip the class score of the image. And you formulated something very similar to before, and we have experiments on MNest and ImageNet as well, where, for example, if we corrupt 4% of the pixels in MNest, we fool it. If we corrupt about 2% of the ImageNet experiments, we also fool the network as well. All right, so future work, obviously, there are so many things that can be done. We can analyze different types of adversarial attacks where the noise is particularly structured in a particular location. We can maybe use these expressions as regularizers. For example, you want to minimize the output variance of the network if it were subjected to some certain types of noise, and maybe even derive deeper expressions for deeper networks and the different noise distributions. So please come see us at poster H19, and there is a code for this on TensorFlow, PyTorch, and MATLAB, and this is the GitHub link. Thank you very much.
To remind, there are 2 microphones, and if you have a question, please come forward and ask it. So I have a question. Have you ever actually tried to harness adversarial examples, and whether this procedure works better for improving the robustness of the network compared to previous approaches?
Okay, so are you asking about if we generate these samples and use them for robust training?
Yeah.
Okay. So one experiment I did not mention is that these expressions were also useful to predict the fooling rate of other adversarial examples, but of course we don't have time for that. But we also have a submission to ECCV where we actually use these expressions as a direct embedded regularizers in the training to better improve the robustness of the method.
Okay, I guess the last session makes an impact. Okay, let's thank the speaker again. Okay, the third paper is about a new pooling operation for deep networks. It is by Faraz, Saeedan, Nicolas Weber, Michael Goesele, and Stefan Roth, who will give the talk.
Thank you, Victor, for the introduction. I'd like to present our work on detail preserving pooling in deep networks. Unfortunately, my student Faraz couldn't make it here because he wasn't able to get a visa to come to the US. So that's why I'm going to give the talk in his stead. So let's jump right into it. Let's look at this image. And suppose I have this nice high-resolution photograph, and now I want to get a downscale version of this. So what's the canonical thing that we might do? We might apply some Gaussian smoothing to avoid aliasing and then to downsample it. But if you put these images side by side and you look a little bit more closely, you will actually see that a lot of the important detail has been lost. For example, the whiskers of the dog in this example. So that's maybe not so satisfying. So let's try something else. This may be better? So this is again our high resolution picture. And now I'm going to do something that maybe sounds a little bit crazy. I'm going to take a small local neighborhood, and in each local neighborhood, I'm going to either take the color that's the brightest or the one that sticks out the most from the environment. And if we now put this side by side, you can actually see that detail has been preserved, so the whiskers of the dog are still visible. However, perceptually, it doesn't look particularly plausible. So you might actually ask, would anyone seriously want to use this? The strange thing is, and you may not be aware of this, but we're probably almost all here in the room are actually using this, maybe not to do downsampling or downscaling, but inside a CNN. Why? Because downscaling is at the heart of pretty much any CNN. We don't call it downscaling there, but we call it pooling. So what's typically used when we do pooling in CNNs? We use max pooling, which is basically what I just described, average pooling, which is what I showed you earlier, or striated convolutions, which from an image downscaling perspective would lead to aliasing. So that seems potentially problematic. Moreover, if you actually look at pooling layers in typical networks, so here, for example, VGG, network in network, or ResNet, different choices are being made, highlighted here in yellow as the default. But for a specific data set, these choices may not always be the best. So if you want to get the most performance out of your network, you may need to do brute force search over the pooling operator. So for this reason, previous work has tried to find ways of overcoming this and learn which pooling is the best. For example, work on gated pooling by Lee and colleagues. And while these outperform standard pooling layers, they don't do that consistently for all networks. So we try to go beyond this. So we're trying to ask the following two research questions. Can we learn from the literature on image downscaling and apply it with benefits to convolutional neural networks? Or, to put it differently, how can we design a pooling layer for CNNs that preserves important detail in the feature maps so that the discriminative power of the network is maximized? So let's get back to image downscaling for a moment. So here we again have our image from the start. And now I show you a solution that hopefully you would agree is better. This is a downscaled version where the detail is actually preserved. And in case you can't see it, here's a zoomed in version. And so you can see that the whiskers of the dog are still visible, but the overall image appearance is still pleasant. So how is this done? For this, we actually turn to a recent paper by Weber and colleagues at SIGGRAPH Asia 2016 called Detail Preserving Image Downscaling. And their idea is the following. They define detail as color that sticks out from the neighborhood. So for example, if you had an all uniformly colored image with a single red pixel sticking out, a typical downscaling method would simply produce a constant image. But that's perhaps undesirable if you want to keep detail. So the way they overcome this is in the following. So you take the high resolution input image. From that, by a naive standard downscaling method, you first derive a guidance image, I tilde, which is basically just obtained by linear filtering and then downsampling. And now you look at what basically got lost by this process. So you take the absolute difference between the input and this guidance image, and this gives you this weight map that you see on the right, which basically shows you where detail in the image has been hiding. Now what you can do is you can do a weighted average based on these weights and obtain a downscaled version where detail is preserved. And this operation, you can think of it as an inverse bilateral filter. So mathematically, what happens is the following. To get the output at a particular pixel p, what you do is that you sum over a neighborhood omega from the input image, shown here in red, and then for each pixel q, you simply average the input pixels. However, you weight them by this weight map that I showed you earlier, which is the absolute difference between the current pixel IQ and the guidance pixel in I tilde. Except that you raise this absolute difference actually to some power lambda. And on top of that, we also need to make sure, of course, that the weights are normalized and sum to 1. So what does this exponent lambda actually do? In fact, it controls detail preserving pooling. So we can now look at an example. Here on the left, you have a high resolution image, and on the right, you have a downscaled version. And now I vary lambda. And you can see that as lambda goes to 0, the averaging tendency of the filter increases. but for large values of lambda, a lot of detail is preserved. So one of the benefits of this is that the amount of detail preservation can actually be adjusted. Okay, so now the goal in this work is that we want to apply this insight to deep networks. So we propose detail preserving pooling, a pooling layer for CNNs that's based on this idea of detail preserving image downscaling. It consists of two different blocks. The first is a linear downscaling block to derive this guidance image, I tilde, which in this case is of course an activation map, which is simply a linear filter followed by downsampling. And then we use that to control the inverse bilateral filter that I mentioned earlier. So let's get into some of the details. So mathematically, we just take a weighted average of the input activations, and now the power comes from the weight function and the way it's defined. So we define it as an inverse bilateral filter, but we make it a bit more flexible than before. And in particular, we take the difference between an input activation, IQ, and the guidance pixel, and we pipe that through a nonlinearity rho, which is a reward function. And we propose two different options for this. The first is a symmetric reward, where the intuition is that activations that are further away from the mean, so from the guidance pixel I tilde, they receive a higher weight. And the function in particular is a generalized Charbonnier function, and it can be controlled by this exponent lambda, which controls the steepness of this reward function. So for small values of lambda, the weight function becomes almost uniform, whereas for large values it becomes steep and leads to detail preservation. Additionally, we add a bias, alpha, which can separately modify the averaging tendency of the downsampling process. We have a second option, which is an asymmetric reward function, which looks very similar, except that at 0 we cut it off and keep it constant below 0. And the intuition here is that we only want to reward detail where the activations are larger than the guidance pixel I tilde. And again, we can control the steepness by the exponent lambda of this function. So then let's look into the second block. That's actually fairly simple. As I mentioned, it's basically just linear filtering followed by downsampling. And in the version that we call light DPP, this is just a box filter, typically 3 by 3 pixels large. In full DPP, we replace this by a learned linear filter, and it's a 2D filter per feature map. And so I mentioned already that we're doing learning. So what does that mean concretely? We want to adapt the behavior of this pooling layer through learning with the normal task-specific loss, for example, cross entropy. And for each feature map, that means that we learn a separate lambda and alpha parameter. It only leads to a relatively modest increase in the number of parameters. In full DPP, we additionally learn a 2D filter per feature map, which typically is 3 by 3 pixels large. And note that these are many fewer parameters than a normal convolutional layer would have. So let's look at some of the characteristics of this detail preserving pooling. One of the benefits is that it's actually fully differentiable with respect to the input activations I, the linear filter F that we want to learn, and lambda and alpha. Moreover, it turns out that DPP generalizes, or more precisely converges to average pooling as lambda goes to 0 or as alpha goes to infinity. And the reason for this is that the weights become equal in this case. Moreover, DPP also generalizes max pooling, so it converges to max pooling for asymmetric weights and lambda going to infinity. And if you recall the shape of the reward function, that perhaps becomes apparent. Interestingly, for the symmetric weight function that I introduced earlier, DPP converges to something that we call extremum pooling, which is basically a simple generalization of max pooling, where instead of taking the maximal activation, you take the one that sticks out the most from the mean, either in positive or a negative direction. So let's get to some results. So here's some results on CVPR18, where we've applied different pooling methods to 3 different networks: VGG, network in network, and ResNet. And one of the things that you can observe is that the default choice highlighted in yellow is not always the best. I mentioned that earlier. However, we find that DPP consistently outperforms these standard pooling layers. And one of the advantages of using it is that you no longer have to do this brute force search for the best pooling method for your particular combination of network and dataset. Moreover, one interesting finding is that the symmetric version of DPP actually turns out to perform the best. So this extremum pooling that it generalizes seems to be working well, and as far as we are aware, this hadn't been considered before. Moreover, if you compare to more advanced pooling methods like mixed pooling, gated pooling, or L2 pooling, we also observe a performance benefit of DPP. So what does it actually learn? So here's some examples for a VGG network trained on CIFAR, and we find that in the earlier layers, the parameters are more similar to max pooling, with a large value of lambda and small values of alpha, whereas for the later layers, the behavior is more similar to average pooling, with larger values of alpha. And in general, one observation that we make is that it's not sufficient to have a single set of parameters, but rather learning them pays off. So let's consider a more challenging task. So here's image classification on the ImageNet dataset, where we take, for example, a ResNet 50 and replace the strided convolutions by DPP. And one of the benefits is that the classification error is reduced quite significantly by 0.8 percentage points here. And this carries over to deeper networks, for example, a ResNet 101. Again, the error is lowered, in this case by 0.6 percentage points for the top one error. The interesting thing is that this is quite a bit more accurate than the much deeper ResNet 152, which has 50% more parameters than ResNet 101, whereas our DPP layer only adds a small number of parameters on top of that, far less than 1%. So in summary, I presented you our detail preserving pooling based on a perceptually motivated image downscaling technique. It's differentiable and learnable. The overhead in terms of computation and the parameters is small to moderate, but the performance improvement, while it's moderate, it's very highly consistent across a wide variety of networks and data sets. And one of the benefits that I didn't have time to talk about is that we can also combine it with stochastic methods. So you can come to our poster to hear more about that. And if you're interested in trying it out, we also have code available. Torch code's already up. PyTorch code will come soon. And now I'd be happy to take any questions. Thank you.
Thank you, Stephen. So this is the last chance for you to ask a question in this CVPR's oral section. If you don't, you have to wait for one more year.
Yeah.
Oh, we have one question there.
Yeah. A problem for the stride or max pooling, there, if you do BP to the image level, you will see checkboard. So this checkboard artifact, can you solve it by using your pooling layer?
That's actually an interesting question. We haven't really looked into it, but what we have looked is actually that at least the translation invariant is slightly improved by DPP by the differentiable properties of the pooling layer. So I'd imagine that it also has some benefit for that, but we haven't actually evaluated this.
Thank you.
So let's thank all the speakers again. So next we are going to do the spotlight sections.
Hello, everyone. I'd like to introduce my work. In this work, we proposed a new loss function called the LGM loss, which is based on the Gaussian mixture distribution. A typical loss is softmax loss, and other losses are proposed to improve it. For example, the contrastive loss and triplet loss, they are similar, and they propose to improve the softmax loss and to minimize the distance between positive pairs. And the center loss tries to record the centers for each class, and they reduce the computational cost. And they all take this form to encourage interclass separability and intraclass compactness. And another loss is proposed, which is called the large margin softmax loss. They try to modify the formulation of the softmax loss to add a classification margin during training, which is illustrated in this figure from the paper. And our motivation, first of all, is to add classification margin. This is illustrated in the original paper. We hope to introduce the classification margin during training with a much easier way. In the large margin softmax loss, a sophisticated function is designed to substitute for the cosine theta, and our formulation is simpler, which will be introduced later. And our second motivation is to model the feature distribution to distinguish abnormal inputs, for example, adversarial and unseen categories. Hopefully, these inputs will have low likelihood in our distribution. First of all, we model the image features as Gaussian mixture model. Then we can compute the loss by the cross entropy between the ground truth and the predicted posterior probability. We use SGD to optimize this loss. And based on this formulation, we can add a classification margin into the formulation, which is simply to minus the margin on the exponent of the ground truth class, which is formulated in this. The margin M controls the size. The margin alpha controls the size of the classification margin, which will help to improve the performance. To encourage the features to follow our Gaussian mixture distribution, we introduce a likelihood regularization term, which is added to the classification loss to form the final formulation as LGM loss. We visualize the features of a mixed training set. On the top row is the softmax loss, center loss, and large margin loss. On the bottom row is our LGM loss without margin, with margin, and the likelihood heat map. We can see that with larger margin, the features tend to be more compact and discriminative. And we also conduct experiments on face recognition and the image classification. For example, on FW dataset with larger M, we can see that the margin is effective to improve the performance on face verification task. And on ImageNet dataset, we can improve its performance too. Another experiment is to distinguish abnormal inputs from the abnormal inputs. For example, adversarial examples. This is the histogram of the inputs. The red is for adversarial examples, and the blue is for normal inputs. We can see on the right figure for our LGM loss, these two different inputs have totally different distribution of likelihood, and we can distinguish them. This is the ROC curve. We can achieve a 3.1% equal error rate to distinguish abnormal inputs and the normal inputs. We can easily introduce classification margin and model distribution and distinguish adversaries. Thanks. Welcome to our post in I1. Thank you.
Hi everyone, my name is Bibi Wu. I'm a PhD student from UC Berkeley. Today I'm very happy to talk about our work, Shift, a zero-flop, zero-parameter alternative to spatial convolutions. Convolutional neural nets have been firmly established as the state-of-the-art in many computer vision tasks. However, the computation complexity of CNN are so high such that they are usually only feasible on powerful GPUs. But they are not usually feasible on embedded devices where the computation and power budgets are very limited. Convolutional neural nets rely on spatial convolution to aggregate spatial information across the image. However, spatial convolutions are expensive because their cost is quadratic with respect to the kernel size. For example, in VGG16 model, 3x3 convolution accounts for 11%, or 50 million parameters, while the FC1 layer, which is essentially a 7x7 convolution, accounts for 74%, or more than 100 million parameters. In this work, we proposed the shift operator to aggregate information efficiently. So shift operator aggregates spatial information by copy a neighborhood pixel towards its center position. And this operation is repeated at all the positions within one channel. And this is equivalent to shifting the entire channel towards one direction. And then we shift different channels towards different directions. So as a consequence, the output tensor, each pixel is going to contain all the neighborhood information across this channel. The shift operation requires 0 flops and 0 parameters. And when fused with one-by-one convolution, it can be implemented by pointer shift rather than data shift. And therefore, it can also avoid memory copy operations as well. So this is a free operation. We use the shift operator to build a family of networks that we call ShiftNet and trained on ImageNet. Comparing with VGG19 model, we achieved comparable accuracy with 34 times reduction in parameter size. And compared with AlexNet, we achieved 77 times reduction in parameter size and get 1.7% better accuracy. We also tested the shift operator on other embedded vision applications. For example, for face verification, we used the ShiftNet-C model to replace the inception net in FaceNet and achieved 35 times reduction in model size, while across different data sets and different benchmarks with at most 1.2% accuracy drop. We also test the shift operator on style transfer by replacing the 3x3 convolutions in the style transfer network with a shift plus 1x1 convolution. We achieved 6 times reduction overall in parameter size, and still we can generate images with similar quality. So thank you, and welcome to our poster at I3. Thank you.
Good afternoon, everyone. My name is Cong Hui Hu. I'm a second-year PhD student from Sketch-X Lab at Queen Mary University of London. Today, I'm glad to be here to share our research work, Sketch-a-Classifier, sketch-based photo classifier generation. And what is Sketch-a-Classifier? As shown, what we want to do is to synthesize a photo classifier using Sketch. And how we can do that? A model regression network will then be trained with Sketch and the ground truth photo classifier of training category. Then we can use the trained model regression network to test on novel categories with Sketch input and generate photo classifier which can tell whether a test photo belongs to that category or not. And why we need Sketch-a-Classifier? Despite the current success in deep neural network, training effective photo classifiers still take lots of examples, like images in the ImageNet dataset. What's more, for some categories, like Asian animals, no photo may exist. So in these scenarios, the applicability is limited. To address these two limitations, many zero-shot learning methods has been proposed recently. But alternatively, what we proposed is synthesizing photo classifier using freehand sketches. This novel problem is challenging because, firstly, to make our model scalable and applicable, the input is only one or a few short sketches. Secondly, from sketch to photo model, this is a cross-domain problem. The sketch and photo model are connected using the model regression network. What makes this problem much harder is that we train it in a cross-category way. We train the model regression network with training category like dog, and either the sketch classifier or sketch feature can be our model input. Then the trained model regression network will be tested on tested category like cat and generate photo classifier for cat with cat sketch. Sketch can also be used to convert a coarse-grained photo classifier into fine-grained. By taking the concatenated sketch and coarse-grained photo classifier as an input, a coarse to fine-grained model regression network can then be trained and test on novel categories like giraffe. These are the binary photo classifier synthesis results. As we mentioned before, both the sketch model and the sketch feature can be our model input. And the feature regression results are better than the model regression results. 5-sketch feature regression is better than 1-shot feature regression and give us the best results. These are the fine-grained photo classifier synthesis results. No matter whether the cost category is none or not during the test time, the regressed model from 5-shot sketch is the best. These are the visualization results. Compared with the ground truth many-shot photo model, the sketch model regressed from sketch feature it can produce the most similar results regarding to the region of interest and important pixels. For more information, please come to our poster in today's poster session in I5. Thank you.
Hello, everybody. Welcome to the presentation, Light Field Intrinsics with Deep Encoder-Decoder Network. My name is Anna Alperovich. I'm a PhD student at the University of Constance. This work have been done together with Ole Johansen, Michael Strecke, and Bastian Goldlucke. In this project, we introduced the first convolutional encoder-decoder network for the light fields that jointly solves disparity estimation and reflection separation tasks. The key idea is to use 3D convolutions to compute features integrated over the whole range of vertical and horizontal epipolar volumes. Later on, we upsample those features into separate decoding pathways: disparity, reconstructed input, diffuse, and specular. Since the accurate ground truth is difficult to obtain, our network performs both supervised and unsupervised training. In order to train the network, we generate light fields, ground truth light disparity, and intrinsic components. So now let's look what light field is. A 4D light field is a collection of images taken from slightly different perspectives. If we stack them on top of each other in a scan line in the camera plane, we get epipolar volumes. If we also fix coordinate in the image plane, we get 2D epis. To construct the input, we divide 9x9 light field into overlapping horizontal and vertical patches. Now let's have a closer look on what happens inside the epis. According to the previous research, diffuse component and disparity correspond to the same projection of the same 3D point. That is share the same pattern. However, the specular component behaves differently as it follows the specular flow, which depends on the local surface geometry. Also, according to the chromatic model, diffuse and specular components sum up to the input light field. To recover reflection components and disparity, we propose a mirror-like architecture that consists of 18 convolutional layers, followed up by upsampling layers for each decoding pathway. Each layer is represented by the residual block that consists of batch normalization, convolution, and leaky ReLU layers. Reflection components and reconstructed input are modeled as 3D decoders, while disparity is 2D. In the last upsampling layer, diffuse and specular components sum up to the input shared features. If ground truth for the input patch is available, the network is trained in supervised manner. Otherwise, only computational costs that come from the chromatic model is used. In total, we use around 160,000 patches, divided into train and validation sets. We distribute the network on 4 GPUs to feed the memory. For all decoders, we use Adam Optimizer and L2 loss. According to the evaluation results, our disparity estimation outperforms some recent approaches for light fields, especially in specular regions with little texture. Our reflection separation works better compared to the modeling approaches for specularity removal and intrinsic images, with albedo and shading combined into diffuse component, and produces competing results compared to the single image CNN. Numerically, we also perform better in some cases for our ground truth that we generated. We illustrate also results that for real-world and synthetic lights that are taken from different sources. To show that our network generalizes well on various types of data. In conclusion, we propose encoder-decoder architecture for multitask learning that supports various decoding pathways. We perform supervised and unsupervised training and achieve competing quality of results for both tasks, reflection separation and disparity estimation. Thank you for your attention, and I would be glad to see you at our poster on I7.
Hello everyone. Today I will introduce our work on learning generative ConvNets via multi-grid modeling and sampling. So the goal of our paper is to learn the energy-based generative ConvNet model of images. The model is in the form of an exponential tilting of a reference distribution. So here Y is an input image. F theta Y is defined by a bottom-up convolutional neural network with a scalar as output. And P0Y is a reference distribution, such as Gaussian Y noise. And we can use maximum likelihood estimation to estimate the parameters of this model. So the gradient of the log likelihood is in the following form. So the problem is that we have an expectation term which is analytically intractable. So we have to use MCMC sampling, for example, the longevity dynamics, to estimate it. The longevity revision has two parts. A gradient descent part to minimize the negative log likelihood plus a Brownian motion term. The challenge is that for image space, P theta is usually multi-model. So the MCMC may have difficulty traversing different modes and may take a long time to converge, which we cannot afford in real learning process. So to address the above challenge, we propose a multi-grid method. Specifically, for each training image, we obtain its multi-grid versions by repeated downsampling, and we learn a separate model at each grade. So at each iteration, we have a sampling step and a learning step. In the sampling step, we generate the synthesized images at multiple grades simultaneously. We initialize the sampling from the minimal 1x1 version of the training image, and the synthesized image at each grade serves to initialize the MCMC sampling from the model of the subsequent finer grade. And in the learning step, the models at multiple grades are updated simultaneously and separately. So the advantages of our models are as follows. Firstly, I'd like to emphasize that this is not another paper on GAN. We seek to address the fundamental question of whether we can learn energy-based models purely by themselves without recruiting extra networks, such as generator networks. We show that it is possible to learn and sample from an energy-based generative ConvNet model with a fixed budget of MCMC. In our case, all we need is 90 steps of longevity dynamics. Another advantage is that sampling at increasingly finer grades is like a simulated annealing process, which helps the MCMC to mix better. The last advantage is that compared to traditional CD learning, our method initializes sampling from the 1x1 version of the training image instead of the original training image. So the synthesized image is much less biased by the observed image. So here are the synthesized results of the model learned from CVPR18 and L-Sum bedroom data sets. So for CVPR18, we train the multi-grid models conditional on each category. We also perform semi-supervised classification tasks using the feature extracted from the learned model, which outperforms the other baseline methods. We also test an image imprinting task where we need to learn a conditional distribution. From left to right are the original image, masked input, and imprinted output. And that's all. Thank you, and welcome to my poster session I9 to discuss more details. Thank you.
Hello everyone, I'm Xenia and today I'm going to present you our article Learning Intelligent Dialects for Bounding Box Annotation. Our task is to train an object detector, and for this we require a lot of training data as state-of-the-art methods needed. Training data usually comes in the form of bounding boxes, which are quite expensive to obtain. If we need to obtain sufficient amount of samples for many classes, it results in years of annotation work. Some faster ways were proposed to collect training data, for example, the work on box verification series. Here, we start with image-level labels and a weak detector is trained. Then we can use the box proposals by the weak detector and verify them. Every verification is very fast, but the number of verifications depends on a number of factors, which I'm going to demonstrate you in the following example. Suppose we have an easy image. Then the number of verifications will be small. For example, if we need to annotate an object of class cat in this image with one distinct object and only few box proposals with high scores, box verification series is the best strategy. On the other hand, if we need to annotate a small object of class potted plant in this cluttered scene, the number of box verifications would be high and then drawing would be a better strategy. In our work, we propose to combine both of these annotation types in the intelligent annotation dialects, which select the best annotation strategy depending on the image, on the class, and the state of the detector. I'm going to show you an example of intelligent dialect for a particular image. If we have a particular image, the intelligent dialect selects which boxes are going to be verified, starting from a long list of boxes that are proposed by a weak detector. For example, here we decided to verify 2 bounding boxes, and then instead of continuing box verification series, we asked the user to draw a bounding box, as we don't have any more good object proposals. In practice, we select a dialect automatically depending on the properties of the problem. And in our work, we propose 2 kinds of agents that try to minimize the annotation time for us. In the first way, we model the expected duration of the episode explicitly by predicting the probability of acceptance for every bounding box and computing the expected duration of any annotation action sequence. In our second method, we use a model-free method, and we use reinforcement learning to learn from trial and error experience and a strategy that minimizes time. We studied many problem scenarios depending on the desired quality of bounding boxes, on the strength of the detector that is available to us, and depending on the technique and time that it takes to draw a bounding box. We were able to show that intelligent annotation dialects both ways perform more or less in the same way, and they both outperform standard strategies, that is drawing a box verification series alone. Besides, we also studied strategies with a fixed number of verifications followed by drawing, and although they work fine in some scenarios, only intelligent annotation dialects were able to adapt to varying problem scenarios. We have some other cool experiments, but as I don't have any more time to tell you about them, please come to visit us at our poster I-13. Thank you.
Hello everyone, my name is Feng Zhou Liao. I'm presenting our work about adversarial attacks. This is a joint work with my Tsinghua University colleagues. Adversarial examples are maliciously designed examples. They are very similar to the original one, but can fool a neural network. Finding a new adversarial example can be thought as an optimization problem. We want to maximize the loss function by changing the input within the restricted maximum perturbation. The most famous method is called FGSM. It calculates the gradient of the loss function with respect to the input and add a scaled gradient back to the original image to get an adversarial example. We can also apply this method multiple times to improve its attackability. This is called IFGSM or iterative FGSM. However, there are two attack paradigms. The first one is crafting an adversary example from a CNN and for the CNN itself. This is called a white box attack. Another one is we can craft an adversary example from CNN1 and use it to attack CNN2. This is called black box attack. Since we know nothing about CNN2, black box attack is closer to real-world scenario, so it is our research focus. However, both FGSM and IFGSM are not good at black box attack. FGSM is a single-step attack, so it is not powerful enough. IFGSM is powerful enough when doing a white box attack, but it is poor at transferring this performance to a black box attack. Notice that with the number of iteration growth, the IFGSM even perform worse and worse. The reason for the poor transferability of IFGSM is overfitting. If we compare model training to adversarial image generation, we'll find that they are actually a very similar process. We know that adding momentum is a good way to prevent overfitting in model training, so borrow it to prevent the overfitting happen here. We propose a method called momentum iterative FGSM. The algorithm is very simple. During each iteration, we accumulate the update direction with a momentum factor mu. Another slight modification is that we normalize the gradient during each iteration. The effect of the momentum is very significant. The solid line shows the black box attack results after applying momentum. We can see that with the number of iteration increases, the number of success rates doesn't decrease anymore. Momentum can also produce more successful black box attacks with the same perturbation level, which means that the momentum method is more efficient. In model training, another method to avoid overfitting is adding more data. Similarly, we can attack more models here. Ensemble attack is a proven method. With the help of momentum, it achieves much higher performance. With the help of the momentum method, we participate in the NIPS adversarial example competition, and we achieve the highest performance in both non-targeted and targeted attack tracks. Thanks. If you are interested in this topic, we also have an adversarial defense paper in this conference, and you can also check it out. Thank you.
Hi everyone, my name is Rich. I'm from University of Maryland. Today I'm going to talk about our work on pruning networks using neural importance score propagation. So our method prunes pre-trained networks. We want to reduce the redundant neurons to achieve fast inference and network compression. So how do we measure the importance to determine which neuron we want to prune or not? Previous method using single layer or two layer statistic like magnitude of weights. However, this kind of greedy layer by layer pruning may lead to error propagation since it ignores the connections between the neuron in the entire network. That's why we want to treat the entire network as a set of feature extractors. So we find that the final responses are really important, since if we can preserve the quality of the responses, we can preserve the predictive power of the network. That's why we want to use the goal of minimizing the reconstruction error of the final response as the way that we measure the neural importance across the entire network. So we formulate the pruning problem as the binary integer optimization. So for any arbitrary layer L, we want to assign an optimized binary vector to determine which neuron we want to prune or not, given a fixed budget, to minimize the reconstruction error of the final response before and after the pruning. We find it's hard to directly do the optimization, but we can simply minimize its upper bound. We have a closed form solution, like we can use the R score, which can compute it from the final response layer's importance score and the weights between this layer and any arbitrary layer L in the previous layers to compute that importance score. So all this derivation is based on the Lipschitz continuity of the activation function of the network. So here is our proposed neural importance score propagation method. So our equation, this kind of derivation enables the one-time feature ranking on the final layer, and we can use this formula to do the propagation of the neural importance from the final layer to the previous layers. Okay, so here's our framework. Given a pre-trained network, we can let the training images go through the network to obtain the final responses. Then we just conduct a one-time feature ranking upon the responses to score them and use that score as the neural importance of the final layer. Then we can use the proposed NISP algorithm to do the propagation of the neural importance score to the previous layer. And given the predefined pruning ratio, which can be determined based on your application, we just keep the top-ranked neurons and filters to obtain the prune network. Finally, we're going to conduct some fine-tuning to retain the predictive capability of the network. Okay, so here we show the figure to directly estimate the average reconstruction error of the final response before and after the pruning using our NISP algorithm and the layer-by-layer pruning, which conducts feature ranking and pruning independently for each layer. We can clearly see that when the network becomes deeper, the reconstruction error of the layer-by-layer pruning becomes much larger. And our NISP algorithm always achieves much smaller and kind of robust performance on this average reconstruction error, which directly meets our expectation of the optimization problem and also explains why our method should work. So in this table, we compare to some other state-of-the-art methods. Some of them are using those magnitude-based layer-by-layer pruning. We find out that given similar accuracy loss, we can achieve much larger flops and parameter reduction and vice versa. And also, you can find out the accuracy loss is very small. Okay, so let's conclude our work. We show that error propagation really exists if we use layer-by-layer pruning. That's why we propose to prune the network based on a unified goal in the backward propagation fashion. And we can achieve significant network compression and acceleration with very small accuracy loss. So please come to our poster for further discussion. Thanks.
Good afternoon. My name is Yi-Zhe. I'm from University of Missouri at Columbia. This is joint work with Li. So the title is Point Grid, a deep network for 3D shape understanding. So the paper is about the 3D representation for deep learning. Right now, the deep learning 3D representation, they are either point clouds or meshes or volumetric grids such as occupancy grid or distant field. So for points or meshes, they preserve the 3D information, but they don't have a regular data structure. So you cannot directly apply 3D scene on top of it. Volumetric grid, on the other hand, is more, sorry, yeah. So volumetric grid, on the other hand, it has a regular data structure. The main limitation is the memory consumption is in general very high, so you can now use a large scale of grid to represent very well the geometric information. So right now, you can only do a small resolution data set. So that's one of the contribution of this paper. We propose a new 3D representation that can overcome some of the limitation. And we call our new representation point grid, which is a hybrid model between point clouds and volumetric grid. So the first step is we give a point cloud, we incorporate or embed a volumetric grid on top of it, so that has a regular data structure. And within each grid cell, we actually sample a fixed key point to represent the local geometry. So compare with other volumetric representation, it can represent more local information beyond just an occupancy mask. So our method beyond has a regular data structure, it can also carry more information. So compared with others, we are more efficient in terms of memory and computation. So we apply our method for like classification, segmentation, and we achieve pretty good result. Yeah, so the left side is this point. Okay, I'll just move to the next one. So the architecture here is a pretty traditional architecture. So for classification, we just use an encoder network. For the segmentation, we use an encoder-decoder network with a mirror link in the middle. So if you see the top left is the point clouds, and we convert it into a point grid volumetric representation. We go through this volume CNN structure, And we have the result in the end, either a classification or either segmentation. And we apply our result, our method on standard benchmark dataset, such as ModelNet or ShapeNet, and we achieve pretty good result. So this is the classification result. We apply on ShapeNet, ModelNet, and compare with other state-of-the-art methods. And as you can see, our method achieve pretty good result on all this benchmark data set. We also show so this is the saliency map to show which part is more important for the classification. So the saliency map is basically the heat map based on the saliency. So the redder it is, the higher salient it is. Otherwise, it's the blue one. So this is the segmentation result. We show a visual comparison side by side with state-of-the-art such point net on the left, ground truth on the right. And so we also do a quantitative mean IOU comparison, and our result seems pretty good compared with all the other methods. So we have a poster at I-19. Thank you.
Hi everyone, I'm Kunpeng Li, a second-year PhD student from Northeastern University in Boston. I'm happy to present our paper, Tell Me Where to Look, Guided Attention Inference Network. This work is a collaboration with Siemens Research in Princeton. We are focusing on attention of convolutional neural network. Using only image-level labels, one can obtain attention maps for input image with backpropagation in CNN. They reflect each pixel's contribution to the final decision. Our work is based on two understandings of attention maps. First, localization information can be extracted from them without extra labeling effort. Second, they can effectively explain the network's decision and help us understand whether the network has learned the right things. Correspondingly, there are two problems we want to solve. First, supervised by only classification laws, attention maps often only cover the most discriminative regions and therefore not adequate enough to serve as cures for tasks like weakly supervised segmentation, where we want to identify regions of each class as complete as possible. Second, network may focus on wrong regions due to dataset bias. For example, for the class boat, the network may be biased towards water due to the concurrence of water and boats in the training images. The generalization ability of the model may suffer when the testing data does not have the same correlation, like boats auto water and water without boats. To solve these issues, we make attention maps a natural component of the end-to-end training, provide self-guidance directly on these maps by exploring supervision from the network itself, and seamlessly bridge the gap between using weak and extra supervision. Attention maps can be significantly improved by our method. Self-guidance is based on the correlation between the attention level of each pixel and its contribution to the final prediction. Two losses work together to build this guidance directly on attention maps. While the attention mining loss is trying to grow the attention region of the target class, the classification loss regularizes the learner so that the attention region covers only the target object. The attention map is online generated and optimized by the two loss functions jointly. For more details, please come to our poster. And our framework can also seamlessly integrate extra supervision. With only a very small amount of extra supervision, around 1% to 10%, the attention maps can be effectively improved. This is especially important when we need to tell the networks which part in the image they should focus on and get them to learn features robust to dataset bias. Quality results of attention map shows that our methods can significantly improve the attention map to cover more complete regions. And we also evaluate our methods on Pascal VOC segmentation sets and find they clearly outperform the state-of-the-art in the same settings. And a very interesting problem, considering the bias in VOC dataset for boats, We constructed another bias dataset with classes of boats out of water and water without boats for testing. We found that our method can help to improve the generalization ability of the network by getting it to focus on the right regions when learning the concept of boat. For more details, welcome to our poster at I-21. Thanks.
Hello, my paper is called 3D Semantic Segmentation with Sum-Manifold Sparse Convolutional Networks. I'm Ben Graham. I'm a research scientist at Facebook AI Research in Paris. Martin's a PhD student at the University of Oxford who did an internship at FAIR Paris last year. And Lawrence van der Massen is a research scientist at FAIR in New York. On the left, you have segmented point clouds from the ShapeNet Core 55 dataset. Each point cloud has about 2,000 points, so at resolution 50 by 50 by 50, they're about 99% sparse. The color shows the segmentation. So, for example, the airplane in the bottom left-hand corner has a fuselage, engines, wings, and a tail. The data was used for an ICTV workshop competition. Because of double-blind submission rules, we can't say if we won or not, but we did better than the people who came second, third, and fourth. On the right is the NYU depth dataset, which you can project into 3D using the depth information. Our approach is quite simple: to take networks that work well for dense data like UNets and adapt them to work in the sparse case. With the UNet, you have downsampling and upsampling. Most of the convolutions have stride 1, and you have a few convolutions with stride 2 to downsample, and some convolutions with stride 1/2 to upsample to give you an output which is the same scale as the input, which you want for segmentation. So our idea is to replace the stride 1 operations with sub-manifold sparse convolutions. So you have the input, some sites are active, some sites are inactive. For each active site, you have a feature vector, which could be RGB or a 0-1 indicator. And for the inactive sites, you implicitly just have a 0 vector. In a regular dense convolution, you scan every location, and so the output has cost proportional to the volume, and the compute is proportional to the volume. We instead just visit the active sites so that the computational cost of the operation is proportional to the set of active sites. And we use a hash table to keep track of what goes where, so checking your neighborhood is like an order 1 operation. So it can be implemented quite efficiently. If you just do sub-manifold sparse convolutions, you don't get very big receptive fields, but if you do a UNet with downsampling and upsampling, you get much bigger receptive fields. So you can see one point on the left of the animation, you can see one point moving around, and we do a UNet with just one downsampling level, one sub-manifold convolution, and one upsampling level, and you can see it's already producing quite large receptive fields. The more downsampling you do, the larger receptive fields you get, which you want to have like a big context when you're doing your segmentation decision problem. Here are some results for the ShapeNet Core 55 dataset. To make it more challenging, we randomly rotate the objects so you can't assume that they have any particular alignment. Dense 3D components are very accurate, but they're computationally very heavy because their computational cost is proportional to the volume. Multi-view 2D components are much cheaper because their computational cost is proportional to the surface area, but the accuracy suffers, so they don't do so well. Our method seems to get the best of both, so the computational cost is proportional to the surface area, but the accuracy is more similar to a dense 3D ConvNet. Our work is available as a PyTorch package, so you can just choose what dimension you want to work in, how many feature planes you want to use at each level, and how deep you want the ConvNet to be, and the spatial scale, because it's sparse, can be anything you like, whatever's convenient. Please come and see our poster at J1, and thank you for listening.
Good afternoon, everyone. I'm Guanyin Chen. I'm going to introduce our work, TomNet, Learning Transparent Object Mapping from a Single Image. This is a joint work with Kai-Han and Kenneth Wang. Given a single image mapping tries to estimate an alpha mat for the foreground object. Then the foreground object can be composited onto a new background. Traditional method works well for opaque objects. However, they cannot handle transparent objects, as object opacity alone is not sufficient to model the refractive effect. Our goal in this work is to introduce a deep learning framework for transparent object mapping from a single image. To make the problem more solvable, we assume the background image is the only light source and the transparent object is colorless. Looking at the background and transparent object, we can see that the transparent object will reflect the light from the background. In fact, we can model this refractive effect with a 2D flow field. For example, the red and green arrows visualize how the surfboard and feet are reflected from the background. In this work, we call this 2D flow field the refractive flow field. By formulating the refractive effect of an object with, say, 2D flow field, the problem of transparent object becomes simultaneously estimating an object mask, an attenuation mask, and a refractive flow field from a single image. We propose a two-stage framework for this task. The first stage, denoted as COSNet, takes a single image as input and estimates an object mask, an attenuation mask, and a refractive flow field. Cross-entropy, mean square error, and endpoint error are used to compute the loss for each output. Image reconstruction loss is also considered to add more regularization on the outputs. As the estimation from the COSNet lacks local details, we introduce the second stage of our framework, denoted as RefineNet to refine the result. Note that there is no output for object mask in this stage, as the estimation from the COSNet is already plausible. Similarly, mean square error and endpoint error are used to compute the loss for each output. As it is very difficult to create a large real data set with ground truth, we render a synthetic data set for training. To validate the generalization ability of our model, we capture a real data set for testing. Note that we do not have the ground truth for the real data set. We report quantitative results on synthetic data set. We report endpoint error, mean square error, and intersection over union on the estimation of flow field, attenuation, and object mask. We can see that our model significantly outperforms the background baseline. Also, the RefineNet is very helpful in the estimation of flow field and attenuation. Let's look at some qualitative results on real data set. The first two columns shows the background and input images. These three columns shows the estimation of our model, the reconstructed image and reconstruction error. The last column shows the composite results. More results can be found in our paper. Our code, model, and dataset are available, and welcome to our poster J3. Thank you.
This concludes the spotlight session. There is a poster session remaining.